Hello and welcome to this video for CE 105-205. So in this video what we're going to talk about is what is governing the glass forming ability of oxides. What governs the ability of an oxide to either form a glass or a crystal when you quench it. And for this we're going to talk about the Zachariasen rules, which is a list of 4 simple rules that you can use to figure out whether a given oxide is more likely to form a glass or crystal. So keep in mind that virtually anything can form a glass if you quench it fast enough, and anything can form a crystal if you quench it slowly enough. So when we talk about the glass forming ability, how easy it is to form a glass with a given substance, we are really talking about how fast do you need to quench a given substance to be able to form a glass. If for a given substance you can form a glass even by quenching it pretty slowly, for example by melting something in a furnace and just taking the melt out of the air and just let it cool based on being in contact with the air, if even with such a slow cooling where the temperature decreases very slowly, the substance is still likely to form a glass, then you have a substance that has a good glass forming ability. It's very easy to form a glass. It's very easy to avoid crystallization. But on the other hand, if it's very challenging to form a glass, if you really need to take the substance and quench it very fast in order to avoid crystallization, then you would be talking in that case of a substance that would have a poor glass forming ability. So the glass forming ability tells you how hard is it to form a glass, how fast do you need to quench the temperature in order to be able to form a glass. And so what the Zachariasen rule will tell you is, for a given oxide system, is it going to be a system that is for which it's easy to form a glass even if you don't quench it very fast, or is it going to be a system for which it's going to be very easy to form a crystal and you would need to quench very fast if you wanted to form a glass. So the Zachariasen rules focus on oxide system and specifically on binary oxides. So when you have a given cation, which can be silicon, boron, aluminum, sodium, calcium, combined with some oxygen atoms. So just to make those rules generic, we're going to write this binary oxide as a combination of a cation A combined with some oxygen O, and we are going to write the fact that those can have different stoichiometry. So for example, we can have M and N for the stoichiometry of the cation and for the oxygen, and the idea in this case is that in each mole of glass or each mole of liquid you would have M cation A atom combined with O oxygen A atom. And so this is pretty generic. So this would apply, for example, to SiO2, where in that case A would be Si and M would be 1. So that's 1 silicon atoms, and N would be 2 combined with 2 oxygen atoms. But it could also apply to something like a calcium oxide or lime, where in this case the cation A would be calcium, and you would have 1 calcium combined with 1 oxygen. So those rules will tell you whether those binary oxides are likely to form a glass or not. And so in this case, silica has a good glass forming ability. It's very easy to form a silica glass, and in contrast, it would be very hard. It's very hard to form a silica crystal, like a quartz crystal. If you take a silica melt and you quench it, most likely you will end up with a silica glass, and it's going to be difficult to end up with a crystal. While on the other hand, calcium oxide, it has a very poor glass forming ability. So in that case, if you take calcium oxide and if you melt it and then you quench it, you will most likely end up with a crystal. It would be very hard, if not impossible, to form a calcium oxide glass. So the question is, what's distinguishing those two systems? Why you have those two systems? They are both oxides. They are both made of cation combined with oxygen. But in one case, silica, it's going to be super easy to form a glass, while calcium oxide, it's going to be almost impossible. What is the key difference? And based on the Zachariasen rules, what Zachariasen is proposing is that the difference between those two systems, you can understand why the one is forming a glass much more easy than the other one. It's because of their atomic structure. And so, for example, if you take silica is made of some silicon atoms, where each of the silicon atoms are surrounded by 4 oxygen, and those oxygen are attached to 2 silicon atoms. So you have a structure like this, where you have the silicon atoms that have 4 oxygen, 4-fold coordinated. They are forming some tetrahedron, and then each oxygen is combined to 2 silicon, and all of those oxygen will be combined with those 2 silicons. And this structure is going to be very likely to form a glass. On the other hand, if you take a calcium oxide, calcium would typically have a coordination number of 6. And so if you take this structure, the oxygen would also have a coordination number of 6 and would be combined with 6 calcium. And what Zachariasen will tell you is that this structure is very unlikely to form a glass. So what we are going to see in this video is what are those Zachariasen rules, what do they mean, where do they come from, and how to apply them to a given binary oxide to figure out if it's an oxide that is going to have a good glass forming ability or poor glass forming ability. So to understand where those Zachariasen rules come from and what is their physical meaning, it's useful to start with what is the definition that was proposed for glass by Zachariasen. And the way Zachariasen defines glass, it defines it as a substance that can form an extended 3D network which lacks periodicity. So there are really 2 things that are important here. First, there is this notion of extended 3D network, and then there is lack periodicity. And those 2 things are really the key foundation of the Zachariasen rules. The first thing is, so the glass must lack periodicity, which means that it should not be periodic. It should not have a periodic structure like a crystal. And the second thing is that it should be able to form an extended 3D network. And when you think about it, those 2 conditions are pretty much opposing each other. So the reason for this opposition is that if you want to form an extended 3D network, you need to have enough connectivity. You need to be able to have the atoms that are connected to each other in a way that is sufficient for those atoms to form a 3D network. For example, if you have some atoms that are just isolated from each other, not connected to each other, then they would not form an extended 3D network. If you have just some atoms forming some chains, so for example, some atoms that are just forming some chains like this, then you would just form some chains that would be a one-dimensional network that would not be enough to form a 3D network. So if you want to form a 3D network, you need to have enough connectivity between the atoms. But you also need to lack periodicity. And so that means, what does it mean to lack periodicity? It means that you need to be able to induce some disorder. The structure needs to be, it needs to be possible for the structure to be disordered, to be non-periodic. And so if you think about this, it means that there needs to be some openness in the structure. The structure needs to be open. If the structure is too connected, then it would be impossible to form a disordered structure. So we will see some example of that. But if the structure is too connected, then you would not have enough flexibility in the structure to be able to form a structure that is not periodic, to form a structure that can be form a disordered network. So if you summarize this thing, it means that if you want to form a 3D network, you need to have enough connectivity. But if the connectivity is too high, if you really have all the atoms being connected to each other with a very large degree of connectivity like this, then you would not be able to form a disordered structure. The only way I could draw such a structure is by forming a crystal. Here, if you have such a high degree of connectivity where each of the atoms is connected to 4 other atoms, there is no flexibility in this structure. There is no way I can move one atom without breaking some bonds. This structure is too connected. It has to remain a crystal. I cannot take one atom and move it left or right without breaking some bonds here. So this structure would be too connected. I cannot make it disordered. It has to remain a crystal. There is not enough, the structure is not open enough to be deformed in a way that it could become disordered. So this structure would be too connected. So even though the Zachariasen rules tells you that the structure cannot be too poorly connected, it has to form a 3D network. The Zachariasen rules also tells you that it cannot be too connected. So there needs to be enough flexibility in the structure. It cannot be too connected, So the Zachariasen rules is really a matter of balance. The structure cannot be too poorly connected, but it cannot be too connected either. So one way to summarize this is that the structure, it needs to be able to form a 3D network. It means that it needs to be connected enough. And so what this means, it means that the structure needs to have some kind of rigidity. The structure needs to be rigid. If the structure was not rigid, if it's not forming a 3D network, then it's very easy for the atoms to move around. If you have just a chain of atoms, then it's very easy for the atoms to move around. And if it's very easy for the atoms to move around, then it means that the substance will have a very low viscosity. It's going to be very easy for the atoms to move from one position to another. And since the crystal always have an energy that is smaller than that of the glass, the structure is always the lowest energy that you can have for a given substance. It's the lowest energy state. And if the atoms are free to move, then they will tend to move towards the lower energy states. Like the atoms always want to achieve the lowest energy state if they can. So here, if you have a structure that is too floppy, where the atoms would be simply forming some chains, for example, and would not form a 3D structure, then the viscosity would be too low. There would not be any kinetic resistance to forming a crystal. The atoms would be able to move very easily. So in that case, it means that it's going to be very easy to form a crystal because the atoms can move very easily. And if they can move, then they will move towards the lowest energy state, which is the crystal. So what the Zachariasen rules tells you is that first there needs to be enough connectivity. This is going to give you a kinetic resistance to crystallization. So this means that if the structure is connected enough, then the viscosity would be high. It's going to be very hard for the atoms to move around. And if it's hard for the atoms to move around, then it means that it's going to be easy to avoid crystallization. The atoms will be moving so slowly that it's going to be very hard for the atoms to crystallize, to reach this stable crystalline state. So that's the first thing. The structure needs to be rigid enough. But the second thing is that it cannot be too rigid. If it's too rigid, if there is too much connectivity, then the atoms cannot move. There is no flexibility in the structure. So that's the second thing. There needs to be some flexibility in the structure. This is to ensure that you can form a disordered structure, a structure that has some long-range disorder where it's not periodic. And this is really a balance here, because one rule tells you that the structure needs to be rigid enough, and the other rules tells you that the structure needs to be flexible enough. So there is really a balance that must be satisfied, and that's really the foundation of the Zachariasen rules. The Zachariasen rules tells you that to form a glass, the oxides needs to have enough flexibility, but also enough rigidity. And this is really only when this balance is satisfied, when you have at the same time enough rigidity to have a kinetic resistance to crystallization, but also enough flexibility to be able to form a disordered network. This is only when those two conditions are satisfied that you will be able to form a glass. So this is really a matter of connectivity. The key thing that matters is how connected the atoms are inside the glass. So if you want to summarize all of this thing, what matters is the connectivity. And so there's going to be an optimal range of connectivity where you can form a glass. But if the connectivity is too low, then it's going to be very easy to form a crystal. You won't have enough kinetic resistance. And if the connectivity is too high, then you will also tend to form a crystal because you will not have enough flexibility to form a disordered structure. So there's really a sweet spot here where the connectivity is not too low, not too high, and this is where the Zachariasen rule tells you that you will be able to form a glass within this sweet spot where the connectivity is not too high and not too low. So since the Zachariasen rule really depends on the connectivity, we need to think about what does connectivity means in terms of structure. And so there is various types of structural features that will govern the connectivity of a glass. The first thing is the coordination number of the atoms. The coordination number tells you how many neighbors each atom is connected to. So for example, if we take the same binary oxide where you have a cation A where you have a stoichiometry of M, and an oxygen combined with some oxygen with a stoichiometry of N, then for example, like a given cation can have a connectivity of 2, for example, or it can have a connectivity of 3. In that case, it will tend to form this triangular structure. Or it can have a connectivity of 4. It can have a coordination number of 4, and in that case, it's going to form these types of tetrahedral structure, where all the angles around would have an angle of 109 degrees. The angle would be 120 degrees if it's from a triangular structure like this. Or, for example, you can have an octahedral structure if the coordination number of the cation is 6. So in this case, you would have an angle of 90 degrees between the oxygen and the central cation atoms. So in this case, so coordination number of the cation would be 6, coordination number of the cation would be 4, coordination number of the cation would be 3, coordination number of the cation would be 2. So in this case, if you know the coordination number of the cation, you can also determine what's the coordination number of the oxygen. There is a formula that allows you to convert the coordination number of the cation to the coordination number of the oxygen. And the idea here is that in an oxides, two cations cannot be connected to each other. The bonds are going to always be between one cation and one oxygen. And the idea is that if you take a given oxides, the oxygen will always have locally a negative charge, while the cation will have a positive charge. So you cannot have two cations connected to each other. The positive charge will repulse each other. And on the other hand, you cannot have two oxygen connected to each other. The negative charge would also repulse each other. So it's always going to be cations connected to oxygen, oxygen connected to cations. So one way to find the relationship between the coordination number of the cation and the coordination number of the oxygen is to count the number of bonds within a glass. So if you look at how many bonds, the number of bonds within a glass, and so for this, that would be those red edges here. How many of those red edges do you have? And one thing that is convenient is to count the number of bonds per mole of glass. So every time you have 1 mole of a formula unit of a glass, how many bonds do you have? So the number of bonds, I can find it like this. I can count the number of bonds by first counting how many cations do I have? So what is the number of cation? And then I can multiply this by the coordination number of the cation. One way to count those bonds is first to see how many of the cation do you have, and then for each cation it's going to be forming a certain number of bonds with its neighbors, and this number of bonds is going to be the coordination number of the cations. So if I count how many cations do I have, and I multiply this by the coordination number of the cation, then I will find the total number of bonds. And in that case, I'm counting all the bonds. Between all the bonds will be comprising one cation. All the bonds will be connecting one cation to one oxygen. So if I take all the cations and I multiply this by their coordination number, I will count all the bonds. There can never be any bond that would not be connected to one cation. So I will not miss any bond if I do that. On the other hand, I will never count a bond 2 times, because there cannot be any bond that would be overcounted. There's never going to be any bond that is connecting one cation to another cation. So I will never count the same bond 2 times. If I take the coordination number of cation multiplied by the actual number of cations, I will exactly count how many bonds I have. But I can also do that with the oxygen. I can say that the number of bonds is equal to how many oxygen do I have, and then what is the coordination number of the oxygen. So it's exactly the same idea. If I take how many oxygen do I have, I multiply this by the coordination number of the oxygen, then I will also count all the bonds, because all the bonds will necessarily be connected to one oxygen and one oxygen only. So if I take the number of oxygen, multiply by the coordination number of the oxygen, then I will also find the number of bonds. So there is 2 expressions here that gives me the number of bonds, and this is going to give us the relationship between the coordination number of the oxygen and the coordination number of the cation. Why? Because here the number of cation, so this is M, there is M cation per mole per formula unit, and the coordination number of oxygen, I'm going to write it like this, coordination number of the cation, I'm going to write it coordination number of A, and there is a N oxygen, and so this gives you a relationship between the coordination number of oxygen and the coordination number of the cation. The relationship between those two only depend on the stoichiometry of the glass, for how many cation do you have and how many oxygen do you have per formula unit of glass. So what this relationship means is that if you know the coordination number of the cation, then you can find the coordination number of the oxygen by this relationship here, for example. So it means that if you know the coordination number of either the cation or either the coordination number of the oxygen, then you will be able to find the coordination number of the other atomic species. So that's the first aspect of the Zachariasen rules, is that we will need to look at what's the coordination number of the cation and what is the coordination number of the oxygen. So the second thing that will be important in the Zachariasen rules, it's not only the connectivity between the atoms themselves, it's also the connectivity between the polyhedra that they form. So the polyhedra is the structure that is formed by the cation. For example, if you have a cation that is forming, that has a coordination number of 3, then it's forming this trigonal structure here. So that would be, in that case, just a planar structure, just a triangle. Or you can have this coordination number of 4, for example, where you have the 4 oxygen around each cation, and in that case it would be forming a tetrahedral structure. So you have this tetrahedral structure here, where all of the angles around the oxygen, around the central atoms, are 109 degrees. And now the second thing is, how are those polyhedra connected to each other? If you have the central cation atoms that is forming either a triangular or a tetrahedral or any other types of polyhedral structure around them, how are those polyhedra connected to each other? And the way that we will measure that, how connected they are, is by counting how many corners of this polyhedra are shared with other cations. So for example, here, this if you take this cation atoms that is forming a tetrahedral structure, it has 4 corners. So those are the 4 oxygen atoms. Those are the 4 corners. The question is, how many of them are going to be connected to another tetrahedron? Some of those corners might be terminating. That means that this oxygen would not be connected to anything else. It would not be connected to any cation A. So in that case, that would be an oxygen that is just terminating, that would not be connected to anything else. And some of those oxygen will be connected to another polyhedra. So they will be connected, for example, another cation that would itself form its polyhedral structure. So here that would be a connected corner. And so the idea here, based on the Zachariasen rules, is that we need to consider how many of those corners are connected to another structure. So there is really like different cases that we can consider here, and the types of connectivity that you can get, typically we refer to this as the QN units. And the idea behind this is that based on how many of those corners are shared, we are going to classify the different types of structure that can be formed based on this QN units classification. So let's see the different case that you might be facing. So the first case is that, so you have, for example, this cation atom. It's forming a tetrahedra with 4 oxygen atoms. So you have 4 corners. The first case that you can face is that each of those 4 corners will be connected to another polyhedra. So each of those 4 corners will be connecting. They will be connected to 2 cations. They will be connected to the central cation, and they will be connected to another cation. So in that case, that's something we will call a Q4 structure, which means that 4 corners are shared. Then second case, now you still have the same cation atom here with still the same oxygen corners, but now the difference is that you have 3 corners that are shared, and you have 1 corner that is terminating, that is not shared with anything else. In that case, we will call this a Q3 structure, a Q3 unit. There's only 3 corners that are shared. So let's see another example. So if you have still the same polyhedra like this, so still the same cation surrounded by 4 oxygen, and now let's assume that only 2 of those oxygen are shared with another cation, then you would have a Q2 units where only 2 corners are shared. So same thing, you could have a Q1 units, and the last possible case would be a Q0 unit. A Q0 unit would mean that you have 0 corners. That means that you would have a cation that would be connected to 4 oxygen, and those 4 oxygen would be isolated. They would be terminating. You would have those oxygen would not be connected to any other cation. In that case, it means that this polyhedra here would be just forming an isolated polyhedra that is not connected to anything else, that is not connected to any other polyhedra. So that would be a Q0 structure. So that's going to be the second thing. The first thing in the Zachariasen rules is the connectivity of the atoms given by their coordination number. The second aspect of the Zachariasen rules is the connectivity between the polyhedra based on those Q4, Q3, Q2, Q0 units. And the last thing that matters in the Zachariasen rules, it's not only how many connections do you have in between the tetrahedra, is what type of connections do you have. So when you have two polyhedra, like for example, if you have like one tetrahedral structure like this, so still the same structure that would be formed by one cation atom that is connected to 4 oxygen around it. So the question here is, how is this tetrahedron connected to the other tetrahedron? So what we saw previously is, if you have 4 corners, how many of those are connected to another cation? But there is a second question, which is, how are they connected? Like, there is different ways you can connect one cation to another. The first way to connect one cation to another is if you have those two cations, where, for example, like this oxygen would be connected to another cation. This cation itself would be forming its own tetrahedron. And so, for example, in this case, this tetrahedron here, those two tetrahedrons would be sharing only one oxygen. They would have only one oxygen in common. And in that case, it means that they are only sharing one corner. There is only one corner that is in common between those two tetrahedrons. So in that case, that would be an example of a corner sharing unit. So in that case, those two tetrahedrons only share one corner. So that's a corner sharing connection in between those two tetrahedrons. But there are some other ways you can connect those two those two polyhedra. Maybe they can share more than one corner. For example, if you have those two cation atoms, and so they are still forming the same types of tetrahedron. So you have one that is forming a tetrahedron like this, and now let's assume that this this tetrahedron is going to be connected to another cation, but this time they are going to be sharing 2 oxygen in common. So now you will have a structure like this, where this is also going to be forming a cation, but this time those two tetrahedrons formed by the 2 cations, they are sharing 2 oxygen in common. So in the first case, they were only sharing 1 oxygen, only sharing 1 corner. Now they are sharing 2 corners. So they have 2 corners in common. And if they are sharing 2 corners, it means that they're actually sharing an edge here. There is an edge that is in common between the 2 tetrahedrons. So in that case, we will call this types of unit an edge sharing unit. So it means that in that case, the 2 tetrahedron will share in common 2 corners. They share an edge in common. And the last possible case that you can have is if you have 2 tetrahedron that will now share 3 corners. So that would be an example like this, where you have one tetrahedron like this at the top that is connected to another tetrahedron at the bottom. So you have this tetrahedral structure here, and this tetrahedral structure would be connected to another tetrahedral structure, where now those 3 oxygen would be connected to the cation, and this cation would be connected to another oxygen. So in that case, you would have another tetrahedral structure like this. And so in that case, it means that now you have between those 2 tetrahedron, they would share 3 oxygen in common. So they would share 3 corners in common. And if they share 3 corners, it means that now they are not sharing just 1 corner, they are not sharing 2 corners, they are not sharing an edge. Now they are sharing a face. So they have one of the face here, the face that is formed by those 3 oxygen would be in common between the 2 tetrahedrons. So in that case, you would call this types of unit a face sharing unit. So you have a face sharing that is shared between the 2 tetrahedrons. So that's the last thing that is considered in the Zachariasen rules. The first thing is the coordination number of the atoms. Second thing is how many corners are shared between the polyhedra, like how many of the corners are shared with another polyhedra. And then the last thing that will matter is what types of connection are created between the polyhedra. Do they share only one corner? Do they share an edge? Or do they share a face? So now, based on all of this, it's time to review what are those 4 rules given by Zachariasen that will tell you in which condition a given oxides, binary oxides, will be able to form a glass. So those 4 rules are going to be giving some conditions, some geometrical conditions or some topological condition. The topology refers to how those atoms are connected to each other. And so those 4 rules will be conditioned, and all of those 4 conditions must be satisfied for the oxides to form a glass. And some of those conditions will involve the coordination number. Some of those conditions will involve how many corners around the polyhedra are shared. And some of those conditions will involve what are the types of connection in between the polyhedra. So the first condition is that the coordination number of the oxygen must be either 1 or 2. So that's the first condition of the Zachariasen rules, is that the oxygen atoms must be linked to only 1 or 2 cations. So what the Zachariasen rules tells you in this case is that you cannot have an oxygen that is connected to more than 2 you cannot have an oxygen that is connected to more than 2 cations. You cannot have an oxygen that will be connected to 3 cations or 4 cations. So those would be forbidden. So remember that the 4 Zachariasen rules needs to be satisfied. So even if one of those rules is not satisfied, then you wouldn't be able to form a glass. So here, the first thing is that a necessary condition, it's not sufficient on its own, but it's necessary, that the coordination number of the oxygen must be 1 or 2. It must be between 1 and 2. If the coordination number of the oxygen is on average lower than 1 or higher than 2, then that would be a condition that is enough to prevent the formation of the glass. Second condition, now it involves the coordination number of the cations this time. And so the second Zachariasen rules tells you that the coordination number of the cation must be small. It must be either 3 or 4. So it has to be between 3 and 4. It can be lower than 3. That cannot be higher than 4. So that's the second rule. Third rule, the third rule of Zachariasen is that you can only have corner sharing units only. So you cannot have the polyhedra need to share corners only. They cannot share edges. They cannot share faces. So it needs to be only corner sharing connection in between the polyhedra. That's the third rule. And then fourth rule of the Zachariasen list of conditions for a substance to form a glass. Every time you have a polyhedra, it needs to share at least 3 corners with other polyhedra. So that's the fourth rule. At least 3 corners of each polyhedra need to be shared. So that's the fourth rule, is that if every time you look at a polyhedra formed by the cation, 3 out of all the corners needs to be shared with other polyhedra. So if you look at those rules, each of them summarizes the fact that the connectivity cannot be too low, cannot be too high. So the first thing here, the coordination number of the cation needs to be 3 and 4. This means that, for example, if the coordination number of the cation is lower than that, then the connectivity would be too low. If the coordination number of the cation would be 2, for example, all you would be doing is some chains of cations, where the cations are just forming some chains like this, where the coordination number is 2. That would not allow you to form a 3-dimensional network. So in that case, the connectivity would be too low. But on the other hand, it's telling you that the connectivity, the coordination number of the cation cannot be higher than 4. So it means that it cannot be 6, for example. A coordination number of 6 would be too high. That would not allow you to form a disordered structure. So that's the one example of the Zachariasen rules, is the connectivity cannot be too low, cannot be too high either. You need to be in the sweet spot of connectivity. The second thing here, same thing, coordination number of the oxygen must be between 1 and 2. It means that, for example, if the coordination number of the oxygen is larger than 2, then you would not be able to form a disordered structure. So, for example, if you have these types of units here where the coordination number is 3, that would be forbidden by the Zachariasen rules. And on the other hand, if the average coordination number of the oxygen is lower than 1, then again that would not be able to, you would not be able to form a 3-dimensional network. So that would also be forbidden by the Zachariasen rules. Third rule tells you that you need to have corner sharing units only. And so one way to see that is that the edge sharing, where you would have two cations sharing an edge like this, so that's forbidden, or a face sharing where you have two cations sharing a face in between them. This kind of thing is also forbidden. So in this case, the Zachariasen rule tells you that you can only have corner sharing. And the reason for that is that if you form edge sharing or face sharing units, then you would not have enough flexibility to form a disordered structure. The two cations would not be able to freely rotate with respect to each other. There would be too much, the structure would be too locked. And in that case, there would not be enough flexibility to form a disordered structure. So the only corner sharing units are allowed by the Zachariasen rules. And the last thing is that the last condition is that at least 3 corners of each polyhedra needs to be shared. And the reason for this is that if you have less than 3 corners that are shared, then again you would not be able to form a 3D structure. For example, if you have a cation atom here that is forming a tetrahedron, and if only 2 of the oxygen are shared, then all you would be able to do is not to form a 3-dimensional structure. You would be only able to form some chains like this, where only 2 of the oxygen are shared, 2 of the corners are shared. That you would form just an infinite chain like this. That would not be enough to form a 3-dimensional structure. So in that case, this condition captures the fact that the connectivity needs to be high enough to be able to form a 3-dimensional structure. So altogether, those 4 rules capture the fact that the connectivity cannot be too low, connectivity cannot be too high. The connectivity needs to be in between those 2 cases. And if a given oxide satisfies those 4 rules, then it's very likely that it's going to be easy to form a glass. But on the other hand, if only one of those 4 rules is not satisfied, then it means that it's very likely that this oxide will not form a glass, and it's going to be very likely to form a crystal instead. So what we will do in the next video, the video just after this one, is that we will see how to apply those 4 Zachariasen rules to review various examples of oxides and see if they satisfy the Zachariasen rules or not.